During my childhood, I remember hearing a lot about the ozone hole. This was about the time that ozone levels had begun to restabilize, but nevertheless it remained in the public discourse. Details, though, were always sparse, beyond phrases like, the hole was caused by CFCs. But what are CFCs? How did they cause the hole? How is the breakdown of the ozone layer reversed? The answer is far more complicated than one or two chemical reactions, so let's get started. Observations of seasonal ozone trends a few decades ago revealed disturbing seasonal losses of ozone over the South Pole, maximized in September and October, the southern spring. This map you see is Antarctica around the end of September, where the hole is biggest. This was 2015. The hole is still there, even though it has begun to recede slightly. These seasonal losses are less significant over the North Pole and basically non-existent in the tropics. Why? For that, we have to look at the process of the South Pole from start to finish. In contrast to the North Pole, the South Pole during fall and winter is isolated meteorologically due to the Antarctic polar vortex. It's also much colder than the Arctic, and at temperatures of less than negative 77 degrees Celsius, polar stratospheric clouds form. Now, chemical reactions on these clouds break down compounds with chlorine in them, which form Cl2. Now, Cl2 doesn't break down ozone on its own. However, in spring the clouds evaporate and sunlight and temperatures increase, which allows the Cl2 to photolyze into Cl, which does break down ozone. Now, as a minor aside, this isn't enough to account for all ozone loss. One more cycle is relevant. The polar clouds also remove HNO3 from the atmosphere, which reduces the amount of NO2 in the atmosphere. NO2 normally removes ClO, but in the absence of this, ClO increases to the point that a new, kind of complicated cycle becomes relevant. Keeping it simple, each iteration of this cycle, which happens as a result of the formation of ClO dimers, it converts 2 ozone molecules to 3 oxygen gas molecules. Anyway, the process of ozone destruction continues throughout the early spring. But in late spring, the vortex breaks up, mid-latitude air mixes in, and this brings both more ozone and more NOx, basically NO and NO2, which converts a lot of the chlorine away. New ozone comes in, which increases back to a reasonable standard that's lower than it was before the winter and spring. And this is the general cycle of ozone depletion. Next winter, clouds will form again, the sun will recede, Cl2 will form, the sun will come, Cl will form, and it will destroy the ozone. Now, this process is natural. This happens in the absence of human compounds, just on a much smaller scale. But the amount of depletion was greatly exacerbated by human compounds known as CFCs, chlorofluorocarbons. How do we know this, and how do we know that our mitigation effects really worked? So these compounds, CFCs, a few of which are shown here, contributed greatly to the depletion of ozone. The Montreal Protocols, enacted in the late 80s, made provisions for the phasing out of CFCs. Scientific data shows that the Antarctic Ozone Depleting Gas Index, a significant component of which is CFCs, peaked around 2001 to 2002. The ozone hole, as we see in this graph, began shrinking significantly around 2005, which is a clear correlation between the two. Looking at the concentrations of individual CFC compounds since 1992 shows similar trends. CFC11 and CFC113 levels peaked and declined fairly early, while CFC12s peaked with CFCs in general around the early 2000s. These trends all correlate and show an expected delay between concentration and recovery. Given how we know ozone depletion works, we can also conclude pretty direct causation between even small changes in CFC concentration on the order of parts per trillion and large swings in stratospheric ozone around the South Pole. Hopefully, this presentation provided a bit more context for a reasonably poorly explained phenomenon. Thanks for listening.